Welcome back to another lecture on speech signal processing. So we are looking at an idea called Word2Vec. This is actually an idea that we discussed last class, but it's an idea that is more from a text processing perspective. But many of the ideas in today's world, whether it's transformers, or you'll hear a lot of these new wonderful progress that we are making. They are all either coming from text or speech or vision, right? These three help each other in many ways. So if you look at the original deep neural networks, the first progress that we made was because of speech, right? So we had this person Geoffrey Hinton, who's very famous, but until he came to Microsoft for a summer, he is a faculty in Canada, and so he spent one summer in Microsoft in I think 2008 or 9, okay, and so with Lee Deng and all these people, so they had a wonderful couple of good coding guys, right, who could code all these things in very well. So Hinton had all these ideas for many years, but they sat and actually said, okay, let us see what happens in speech. And it made a big jump, right? I mean, so before that, even we were, always in this competition. So we have the standard data sets, and we'll say, oh, we improved from 27.5 to 27.1, some 0.4% improvement, or 19.3 to 18.9. We are very, very happy with such progress, okay? And then suddenly in 2009, so this happened for a period of about 7-8 years where we were doing incremental kind of progress. And then in when Hinton came and spent that lab, suddenly from somewhere around 19%, what is a good progress at that age, at that period of time? They would have said 18.5, 18, 1.3% improvement, 17. No, it came down to something like 12 point something, right? So about 6-7%. I mean, it reduced the error by almost 1/3. Okay, never heard of such big progress, right? And that's when people bought the idea. Okay, neural networks can do something wonderful. Neural networks have been there for a long time. They have their cycles. Even early 1990s, people were excited, but it somehow didn't perform as well as the classical methods, right? But this was first time where it beat the classical methods, really by a big margin, okay? And then DNNs were there for some time, and then we will see the CTC came, right, which we have discussed a little bit. So directly we could go from waveform, from feature vectors to characters itself, right? And then this that is around 2012-13. Then Word2Vec came. Now this is coming from a text perspective, okay? So this idea was in text, and then RNN language model came. That also is from a language model, given a sequence of words, text, right? Given a sequence of words. So RNN language model, we work a lot closely with that group in Brno, right? It is a Czech group. They are a big, wonderful group, and so Miklov is a student from there. And that made, so now you can see speech made one jump, then RNN language models made a big impact, right? Then Word2Vec, which we will see now, was also very, very useful in its own way. And so, and then vision, later on you will see ideas from there's BYOL and Barlow twins and all these things. Some of them come from vision also, and many of these things, SimCLR, they are also going to help somewhere in the audio space and so on. So it's always one field does some progress, the others try to copy that or mimic that into the data sets are essentially different, right? Speech is one kind of data set, text is another kind of data set, and then images are another type of data set, right? So what is this Word2Vec? If you remember, I told you the basic idea in Word2Vec is we had this one hot vectors, right? So with one hot vectors, you cannot do something useful, in the sense there is no relationship between words, because every word is in that 90-degree parallel, perpendicular to each other, right? So in a 100,000 dimensional space, there are 100,000 dimensional orthonormal vectors, and therefore they are always equidistant from every other word, right? But we know that man and king, queen and woman, there is some connection, right? And this is what Word2Vec actually found out. Not only could they reduce the dimension, right, but they also found some very interesting relationship between these kind of words, right? So which I am projecting now. this is where the beauty of Word2Vec became even more interesting. So, if I look at the distance between the word France, the embedding for France, we are already doing the embedding from a one hot vector of 100,000, we come through the embedding matrix to some, let us say, 500 dimensional vector. Paris is also 500 dimensional vector. If you look at the distance between these two, or the vectorial distance, and between London and England, they will be very similar, right? And why is it? And similarly, if you look at Rome in Italy, or if you look at New Delhi and India, they all will look very similar. What does that mean? It means that the representation has learned that Paris is the capital of, or there is a relationship. Paris is the capital of France, London is the capital of England, Rome is the capital of Italy, New Delhi is the capital of India. So, whenever the capital kind of relationship comes, it sort of is in the same direction, okay. And that is very, very beautiful, right? I mean, it's capturing some information that is intuitive, right? So, and we just learnt it, right? We asked a neural network to predict some in between missing word, and from that embedding itself, this kind of relationships evolved, right? So, therefore, this is something that I will again talk about. So, there were two problems with one hot representation for words. One is it is not very efficient, the other is all words are equidistant, right. So, we are now, I am just going to summarize what we said, but now in a much more summarized way. So, one thing we did was that we took this example of the cute, right, and then we said cat, right, jumped over. So, we are saying given two words before and two words afterwards, and these are still one hot representations, can I predict the word cat? Or another example could be cute cat, right. The next now I can make jumped the missing word, right, jumped over the, right. All of these, how do I do? What am I going to do? I am going to say the, I have one hot vector, cute I have one hot vector, then jumped I have one hot vector, and over I have one hot vector, right. The cute, right, jumped over, and what I am going to do is, this is like a weight matrix, the E, which will reduce it to a, this is like the hidden layer, right. So, now we are reducing it to a very small set, let us say this is 100,000 cross 1, right. This is the one hot vector, I am reducing it to 500 cross 1, right. It is a very small dimension, right. And similarly, the same matrix E applies on this guy also. We are going to learn the same matrix applies on this also. The same matrix applies on this vector also. So, we can add, I mean, basically they are all going to, so it is an average kind of thing. But what is my task? My task is to predict cute here, cat here, right. So, cat is one of the 100,000 words, right, 100,000 class problem, right. So, I have to give some target, I have to say cat is here 1, all the others should have 0 probability, only this should have 1 probability, and that is what is we are going to say softmax we are going to apply and do cross entropy kind of thing. So, we have a softmax somewhere sitting here, right, and basically we are going to now expand it from 500 back to, let us say 100,000, right. So, what is the task? The task is I am given the cute jumped over. So, I am given the context and I am trying to predict the missing word, right. From these left two words and right two words, I am trying to predict cat, and how am I going to do? I am going to initialize E, the embedding matrix randomly. This is like a random weights. This is like a weight matrix. W is also a weight matrix. We randomly do it. We forward pass, we will get an error, then we backward pass and keep doing it. But remember, there is no non-linearity per se in any of this, because this embedding is just a matrix multiplication of E with that one hot vector, and W is again a matrix multiplication to go back to the 100,000 dimensional space, except that we will apply some kind of a softmax to make sure that we correctly classify the cat. Okay. So, that is the only issue that we are trying to do here, right. And this is a basic idea we are trying to do, and in fact, this also softmax is not necessary, it is actually going to expand and give you the correct 100,000 dimensional vector. That is what we are going to do. We are going to fit the two vectors, and that error is what we are going to back propagate. Okay. So similarly, I will do cute and cat. Now I have to and over and the. So given these four words, cute and cat, left context, over and the right context, can I predict jump? I do this for many words, and then after the network has learnt a lot and it doesn't improve anymore, E becomes a fixed matrix, W becomes a fixed matrix. So now every guy can be represented. So E is the embedding matrix. So after training Word2Vec, right, you are going to get an E matrix, right, E embedding matrix. This is the embedding matrix. And then for any word, what do? I take E, this will be some 500 cross 100,000, and then I apply the corresponding one hot vector, let us say the, and I will get the E of the, right. This will be 500 cross 1 vector, right. Or I am going to apply something more, or I apply E remains same, but now 1 of cat will come, then the E of cat, the embedding of cat will come. So every one of these, this is basically what we call as principal component analysis. Okay. So but this is one idea, and secondly we saw, so this is doing the dimensionality reduction, right. So dimensionality reduction. That was one task we are interested. This is very very sparse, right, or one hot, not a very efficient representation, right. But this is actually a dense vector, right. So that is very good. It is only 500 dimension, all of which are non-zero, and it carries a lot of information. Secondly, we also see that that there is some connection between the words, right. So there is so what does it mean? That is in the original one hot, okay, in one hot space, if you look at this guy, one hot space, if I look at apple, orange and man, right, they were always lying like this. So this was 1 0 0, this was 0 1 1 0, this is 0 0 1, right. So this was apple, this was orange, this was man, right. But now in the embedding space, let us say embedding, let us say I reduce it to 2 dimension, from 3D I go to 2D. This is dimensionality reduction, right. Now if it so happens that it is like this, sorry, now I have gone to 2D, right. So the third dimension is obviously not there. Let us say these are the 2 dimensions, right. So if I am in the 2D space, so the embedding matrix, what will it do? So E of apple is 2 cross 1 is E of 2 cross 3 and 1 hot of apple, right. That is how it is going to be, right. So in this 2 dimensional space, apple might be here, orange might be here, and man might be here. Now this is more meaningful, right, because apple and orange are close to each other, apple and man are very far away, right. This is what is happening in the embedding space. Originally all of them were at square root of 2, all of them were at square root of 2, they were equidistant, there was nothing that one word was more closer to another word. On the other hand, in the embedding space, this is actually connecting words that are close to each other, in some sense closer in the space, and those that are far apart are further in space. So the second problem is also there is that all words are not equally far away from all the other words in the vocabulary. Some words are closer to each other in the embedding space. So this is a beautiful thing that happened. So, both of them are something that we wanted, right? We wanted to reduce the dimensionality and we wanted some connection between the words, and this Word2Vec is able to achieve both of this. So, it was how, I mean, achieve in the sense it does do it. So, that was the remarkable part. They tried to learn the embedding this way, and fortunately the embedding turned out to be a very good principal component kind of an analysis with bunching towards words that are closer in some semantic sense. Okay. Now comes another important idea. In doing this, I am actually not using any supervision, right. So, how Word2Vec is learned? So, Word2Vec just uses one hot vectors, right. And it does not assume any in this kind of training, in learning embedding matrix, right. It does not use any human supervision, any manually annotated data or anything, right. Does not require any manually annotated data, right. That is, it is not, I mean, the supervision is it is supervised learning in some sense. Why is it supervised? Because I am telling what it should learn, right. So, I am telling, can you predict the correct missing word, right. So, it is supervision, but I am telling can you predict, but I also know the word, but the word came from the original text itself, right. So, that is why it is often also part of the self-supervised learning, right. So, basically supervision comes only from the directly from training text, right. So, basically this is also supervised is is coming from the training. So, it is self itself. So, we call it a self-supervised learning. Okay. Why am I pointing out? Tomorrow or a few days later you will hear some amazing thing called BERT, which has changed the whole NLP space and all that. But if you had looked at Word2Vec, right, if you look at this idea, it was very obvious what to do for BERT. Okay, it's not, but suddenly I mean the connection, what I'm trying to say is, in retrospect now, if you look at it, if I knew Word2Vec and if I thought for a little while, you will immediately see BERT is an obvious thing to do. Okay, but when BERT came, it revolutionized at the NLP space. But actually, a lot of these ideas are built on other ideas. So, it's not suddenly that BERT came up. They came up with the BERT. Somebody like Word2Vec, I mean, Google guys were working for some time. They already had this idea. And they said, "Oh, I've seen similar things. So why not apply this to this problem?" And hey, it made a big difference. Word2Vec itself made a big impact, but made even more bigger impact, right? So, but it's not like miraculously like suddenly you got serendipity and you did. It's acquired knowledge. You do research every year. You find some new interesting ideas, and all that gets absorbed. And then you will see 2 years later, haven't I done something similar like this? Maybe should I try like that? And then you see that you can get a good idea maybe, right? So, these are actually this whole, now today everybody talks about self-supervised learning. Well, this RN and LM and Word2Vec, they are all self-supervised learning methods only, right? There is no manual annotation that you are actually doing, correct? So, this is one thing that I wanted to mention. So, we will come across this. You will see that here also, if you should remember this step, because BERT is closely related to this idea only. Okay. So, BERT is essentially this but a more generalized form, right? And there also you are trying to somehow try to predict some word given some left context and right context. Okay, here we gave 2 or 3 words left and right. Okay, and there are even 2 strategies, CBOW and skip-ram. I am not going to the details of Word2Vec, but essentially if you look at this, you should immediately, when I start talking about BERT, you should start seeing the connection. Okay, so I will come to it maybe in a few classes. Okay.